Hello, I'm Jack Price, and my presentation is on the hazards of Martian soil and beneficial uses for future missions. It's impractical to attempt to separate humans from soil, even on another world. That said, in order to live and discover the mysteries of this new world, humans will need to rely upon the soil for its benefits, but will need to abate its deficiencies. These challenges will be discussed in detail later. So to set the agenda for the course of this presentation, we'll talk about the importance of soil on Mars as it is on Earth, some general background knowledge on Martian soil, the presence of perchlorate in Martian soil and how to treat it, the effects of Martian dust on humans and equipment and methods of clearing it, and finally the use of soil as a natural resource. Soil is important to daily life. This fact will follow humanity to Mars. Soil is vital on Earth for a couple of reasons, including the fact that most structures are placed on soil. It enables agriculture to feed a world population and can be used as a raw material, such as in fine aggregate in concrete. Off-Earth, soil would be most immediately useful as a landing zone, but it can also be used as a raw material for reducing overall mission costs or even a self-sustaining colony. Some selected physical properties of Martian soil will now be given in order to better understand the later topics. The top layer of Martian soil is known as regolith. It is comprised of particles resulting from asteroid impacts and are distributed by Martian dust storms. There is some limited data on mechanical properties of Martian soil, including an observed lack of cohesion and a 21-degree friction angle range. The bulk density has also been determined by robotic probes. Perchlorate is a chlorine oxyanion that occurs naturally on Earth, but is most commonly found in the environment near munitions and rocket manufacturing sites. The EPA has imposed allowable levels of perchlorate in soil to 55 parts per million. Consequences of perchlorate exposure over time are mostly linked to hypothyroidism, or an inactive thyroid gland. Symptoms include enlarged thyroid, irritability, depression, lifetime cancer risk, and miscarriage in pregnant women. Miscarriage is of particular concern for any colony attempt. Martian regolith contains 0.5% perchlorate by weight, equivalent to 5,000 parts per million. This is 91 times the EPA limit. Plants accumulate perchlorate and can render crops inedible. Merely 121 grams of food per day grown in contaminated soil can be safely eaten. Therefore, treatment of affected soil will be required for any agriculture to be done on Mars. Treating the soil will result in contaminated water. Fortunately, there are existing technologies that can reduce perchlorate levels in water. Of particular interest are phytoremediation, which uses plants to collect perchlorate, and bioremediation, which has demonstrated complete microbial destruction of perchlorate when given a source of organic carbon. Collection of perchlorate may be desirable if it is to be used as a chemical feedstock. Martian dust is generated by collision weathering and is dispersed across the planet by dust storms. Experience with dust in human spaceflight dates back to the Apollo missions. They gave NASA first-hand experience with the damaging effects of dust on other worlds, leading to spacesuit seal fouling and astronaut discomfort. Tests on lab mice have found that the effect is more than mere discomfort. In severe inhalation cases, the lining of the lungs is actually dying. Experience with Martian dust is limited to rovers and other probes, but their failures have historically been the result of dust blocking solar panels from receiving enough light to generate electrical power. On the next slide, dust removal strategies for the inside of the habitat and outside will be discussed. On the outside, wind can clean a small amount of dust from surfaces, but will need to be supplemented by a more active approach. Surfaces can be swept clean, dry or with some sort of lubrication, be blown clean using compressed Martian atmosphere, be covered, or be cleaned with an electric field. Inside, more traditional methods of dust collection can be used. Depth filtration and gravity settlers are not likely to be efficient, as filtration requires expendable filters that would have to be launched from Earth, and weak Martian gravity reduces the effectiveness of settling. Electrostatic methods are promising, as they can be run using the same system as an outdoors electrostatic dust cleaner. For a less expensive Mars mission or self-sustaining colony, Martian soil will need to be used as a resource. It can be used as a radiation shield or to reduce stresses on pressure vessels. It can be mixed with sulfur and heated to produce a high-strength 68 megapascal concrete. By comparison, a typical concrete strength is around 28 megapascals. The soil can be used in agriculture once suitably treated for perchlorate, and it can even be used as a source of raw materials. In summary, Martian soil presents some difficulties for future Martian explorers. It contains perchlorate, which can lead to long-term health consequences if the soil is not treated correctly. The fine particles of Martian soil form a dust that can adversely affect astronaut health and can even damage the equipment their lives depend on. Fortunately, the solutions to these problems already exist in some form here on Earth. Perchlorate can be collected, or it can simply be disposed of with bioremediation, and dust can be efficiently removed with electrostatic systems. Martian soil can also be used as a source of raw material for meeting the needs of colonists or even in reducing costs on an exploration mission. Thank you.